Should I start? Okay, thank you all for coming. Today I want to talk about simplicity and differential core. I wanted to prove theorems, and you can see that differential core have a similarity with Cartier core, and this simplicity with the F regularities. So before that, I should explain some basic things about the differential, what is the ring of differential is, and some theorems before I go through these parts. So first definition. For the rest of talk, I assume that R and A are commutative rings. So R is commutative. And A that's a subring of R. So the differential operator of R of order n is denoted by dnr over R, the subset of R. We define it as follows. Actually, we defined it inductively. D0 R over R is equal to R comma R, and Dn is delta in A or R such that we have this commutator in D n minus 1 R over R in R. And by this commutator, I mean that the delta R minus R. So if I wanted to talk generally about, before that, I should mention that dr over R, we call it ring of differential operator, is the union of the n's R over R. For every n is the natural number. So more generally, if we assume that m and n are modules, so Dn R over R and dr over R, both of them are submodules of A or n. So it's exactly the same. We define it exactly the same with these same rules. So first of all, the zero over R and the n over R and n is delta in over R and n such that delta ORm minus delta Rn or delta is in D n minus 1 R over R for R in R. And by Rn, I mean that multiplication for R in module n, and exactly the same for Rn. So there is some interesting properties here, as Pedro said the other day. Dn R over R and Dn is a subset of Dn plus n, and Dn minus 1 is a subset of Dn. But before I go through the other parts, maybe I should give an example. So, example is that we assume that R is a polynomial ring with n variables, such that the characteristic of R is 0. So the ring of differential operator of this polynomial ring is called, it's not partial over partial control. And the ring of differential operator is exactly the same as the reactor. Okay. Now I wanted to talk about PNR overall. PNR, as always, we assume that R is commutative ring, A is a subring of R. So PN, I mean that module of principal part, and I define it as follows: that R tensor R over R, delta n plus 1 R over R. And delta R over R is the kernel of this multiplication map. R tensor R goes to R over R. So Pn R over Rn, we define it as R tensor n over delta n plus 1, where delta R over R n is equal to delta R multiplication by R tensor. So these two models is actually R tensor R models. And I should mention that these two models, even if R is Noetherian, these two models may not be finitely generated. But if R is essentially a finite type over R, then both of them are finitely generated. Okay. There's an important theorem that relates these models with differential operator. Dn(r) over R, we have this isomorphism that Dn is isomorphic to R, Pn R over R, En, and N. So we have this isomorphism, so in this case you can commute the ring of differential operator more easily. And there are interesting things about this ring of differential operator, but I wanted to skip this part because it takes too many time for us to talk about that, and I go through the ideas. We say that the ideal and we say that R is D R over R simple if it has no proper D R over R. And sometimes we say that we say that D simple. If I take D simple, I use. And we say that R is D module simple. It's just a definition that comes from the simple things, a simple module or simple ring. So there's nothing less. I just wanted to mention. R is D module simple if it is D simple one. So I mean that there is no proper D ideal except 0 and R. So I have a little bit. Yeah,
so I'm confused. Why is this different from the previous definition you gave? So you define what it means for R to be a D module simple.
Here, I think as a ring, and here are the moon. I just wanted to, I told you, I just wanted to mention that this is the same.
Okay.
Because,
Okay.
yeah, I know it's the same. I just wanted to specify this definition because I wanted to use that.
Okay.
So there is a bijection. There is a natural bijection between these two sets. A is I, the subset of R, such that I is integer and I is PR over R ideal, and B is equal to J subset of W minus R, such that J is D W minus R. So you can see that we can commute with the multiplicative set. Another number, it's very important because I wanted to use that for proving the differential code. So every minimal primary component of D over R ideals or D over R. Okay. And another level that if for every R in R minus 0, there exists some delta in R over R. It is property that delta R is equal to 1, then R is the module. And actually the converse holds true. Okay. If you have a question, do you have any question?
So the arguments, they are also usual ideas.
But it's property that.
Oh, yeah, it's an extra figure.
So I need a definition here. Is that we assume that as a usual R is a ring and A is a subring. We say that I is an ideal of R and N is a positive integer. The A linear and differential power of I. We define it as follows, that I n over R is equal to F in R such that delta of F is in I for every delta in the n. And we use this definition to describe the differential code. So before I go through the definition of differential code, I should mention some properties of this differential power. So properties. First of all, this IN is ideal. If I is a subset of J, then IN is a subset of Jn. The intersection of I alpha n for alpha in R and collection of ideal is equal to alpha to the power of n, I to the power of n is a simple, just power of n always is a subset of differential power. If I is prime, then the simple power of n is a subset of this one. And I n W is equal to W minus 1 to the power of n. And is that if R is P primary, then In is P primary. What else? Okay. We have that I to the power n plus 1 is always we have this subset here. Okay, and it's removed plus 1. I is P R over R ideal. If and only if n is equal to 1 R for every n together. And this condition is important because it's not true if we say that just some n should be bigger or equal than. So definition of this talk is that we assume that R and n are locally, as usual, R is a subring of A, R, and J is an ideal of R. So differential for of R, we define it as follows. Is equal to the subset of J to the power of n for n that is natural number. So this is the differential definition of differential code, and as if you remember, Javier told us that Cartier code is that Ka that is subset of n natural number that is equal to this one. So you can see that this is the similarities.
I have a little question. For the definition, you don't need R to be local, right? You can just.
But this is the differential curve of J. And we should talk about differential curve of R itself. So in this case, differential curve of R is equal to this. We mentioned that this is the maximal value.
That would be the analog of the splitting prime or local prime. Yeah.
So the properties of this differential curve is that first of all, for J is P R over R ideal. The second law is that if I is a subset of J and I is P ideal, then I is a subset of rho of J. If J is prime, then rho of J primary, and 4
It's primary. It's not prime.
is primary.
Do you have example that it's not prime?
I don't have an example, but I know that this is primary, not prime. Because especially rho J, I mean that this one is primary. It's primary, not prime.
Oh, that's so sad. No.
And
Yeah, it's sad.
yeah, in my notes.
That's so weird, but continue.
Yes. And R over R is visible. I wanted to prove these properties, but before that, I should mention something that you can see the similarity between cartesian core and differential core.
So 2 says that P is the largest, the ideal containing J.
As we have in the
Yeah.
chart. I just wanted to mention here.
Yeah, no, it all looks the same, but it's 3.
I thought
Okay.
So,
We'll see later.
this is the property of cartesian core. I wanted to mention, in this case, you can see the similarity between differential core and differential and cartesian core. So, we have that the one is 1, then R over P, and P is equal to 2, and we will R, the intersection of this are the same. If C is in IRF, RFP is contained in A, then C is contained in P of RFP. And the last one is that if P is memory on A, then P is a subset of A, and in particular, if A is in RRP, then A is equal to well, you can see the similarity between this Cartesian core and differential core. The only thing that I can find that is similar is this.
Oh, yeah, so far they share similar properties. It's just like on one hand you have the ring of Hercule operators, acting on R. On the other hand, you have the ring of differential operators, acting on R. And they share similar properties so far.
Yeah. But not all the subjects. For example, you talked about the Lambda, and this is some of these, but I couldn't find anything that is I can relate these two parts together.
Oh, no, probably that hasn't been written by anyone. Well, so far very shocking to me is 3. That is not prime.
No, it's not prime, it's primary.
Well, let's see.
So I'm going to prove these properties here. The first one is that we assume that F is in rho or J, and delta is Dn. So for every sigma in Dn or over R, we have this property that sigma delta is in D and plus F over R. So since F is in J to the power of plus N for every N in N, so we have that delta, the sigma delta multiplied by F is in J. So therefore delta F is in J to the power of N for every N in N, and we can see that delta F is in rho R. So we can see that differential core is the idea. For the second part, we assume that I is a power of J, is a subset of J, and I is P R over R ideal. I said that if I is a subset of J, then IN is a subset of Jn. And so for every n, we have this property. So, and I said that if I is a D ideal, then I is equal to IN. So in this case, we have this equality. And this is equal to rho r. I actually need to take a shower. So the third one is that we assume that P is prime, minimum prime of rho Rj. Since J is prime, and rho Rj is a subset of J, then we have that P is a subset of J. So let Q be primary, P primary component of rho J. So in this case, we can say that we can render rho Rj as the Q intersection with the some primary ideals. Then Q, then rho Rj is a subset of Q is a subset of J. Then I said that I said the lemma is that every minimal primary component of D ideal is a D ideal. So in this case, Q is a D ideal. So according to the second part, I have that Q is a subset of rho Rj. So Q is rho Rj is primary.
So, so actually, have a question then, like, do we know whether or not the ideals are radical if something like this? Because that seems to be what is missing, because if that were true, that would force P to be prime.
I don't know. I didn't see anything about the radical ideals of the ideals.
Yeah, because for Cartier, it's not for free. Like you need some assumption on the purity.
Yeah, I saw your paper and you talked about that if it is radical ideal, it should be prime. But I couldn't find anything yet.
Okay, yeah, but we'll see.
The only paper that I checked about the D ideals, anything that said is just this property, not anything more.
Okay.
At least until now. So the forward, we wanted to prove this simple. So we assume that for contradiction that is not this simple. So there is integral is R over 4A, which is this integral under differential operator. So in this case, there exists P R over R ideal that contains rho Rj. So in this case, according to this part, we have a contradiction. So, okay. I just wanted to remind something in prime characteristic. Do you have a question? No. About prime characteristics, so just a reminder. We say that R is strongly irregular if for every R in R minus R zero, the exists in N such that the map is from R to R from 1 to 4 and as a remark, we know that R is strongly irregular if and only if R is a product of a strongly irregular group. And the theorem here is said that is perfectly and R is essentially a finite type over O. Then the ring of differential operator is this union of a critical number of D. We denoted this homomorphism by D, and if you remember that, I said that if R is essentially a finite type, then this homomorphism should be finitely general. So D is a finitely general. So as a last theorem, that belongs to Smith, we will prove that assume that R is finite. F or is irregular if and only if R is product of a simple number. So I have this remark. We said that R is strongly irregular if and only it is a product of domains. So in this case, we reduce the domain case. So we know that R is strongly irregular if and only if for every R in R minus 0, there exists P in N and P in form of PE, such that P of R is equal to 1. And we know that this inclusion that PT is a subset of R. So by post-composition of these two maps, the post-composition of these two maps gives us that we have PT in the E, such that the R is equal to 15, R is equal to 1. So if you remember the lemma about the D modules, so R is simple map. Again, for the opposite case, if R is equal for every R in R minus 0, here in the E such that the field of R is equal to 1. So let the R is from R to RPE, that is RPE linear, such that theta 1 is equal to 1. Then theta of the field is in harm RPE, RPE. So such that if I see that this is C, here R is equal to 1. So R is strongly identified. This is
I see. I thought it was a much more difficult. Well, it's really based on that theorem one.
yeah, but proving this part is so difficult. I should mention something else. So I didn't prove this part.
Okay. So you're done? Oh, that was quick.
I tried to speak very slow, but I couldn't.
So then I have a question, like, so does this mean that the differential core and the Cartier core are the same thing, positive characteristic, or we don't know that? Because here you prove that they are trivial at the same time. What is trivial if only the other one is trivial? But would it mean this like they are the same in positive characteristic? I'm sure probably it's not written down anywhere.
No, I didn't.
But would you believe that's the case? Like they are just literally the same?
I think that they're literally the same because they have the literally the same properties. Anything, as I mentioned here, anything you see, you set for the differential, for the Cartier core, you can see in the differential core.
Yeah. Well, yeah, with that theorem one, and based on how this proof works, they could give this the exact same result, but I'm not sure. So, but yeah, so I guess it would be cool if we can figure it out. Is it your homework then? So yeah, this is great. I hope you guys see that it's something cool. I would like to know more, like if it's to what extent they're really the same thing. So actually, I have another question here. This looks promising because yeah, for that D, because I don't know if you remember if at some point in class I sort of asked you, like, we know that fees in the Cartier theory side correspond to these boundaries and so on. Then I wonder, like, and I asked you, like, what differential operators would correspond to, if by any chance they correspond to any boundary. But this suggests that it's a positive characteristic. This is the case. In characteristics here would be a bit unclear for me, but that's another question to think about. Because actually on the right hand side is home from R to R. I think they can be made in batteries of some type. I don't know. But yeah. So yeah. Well, we can stop here and maybe we can talk later next time.
Yeah.
In our usual meeting. But yeah, well, thanks. I don't know if there are questions.
Yeah.